Let's denote the given equation of the pair of straight lines by 1. Now let the equation of the two lines represented by equation 1 be y is equal to m1x plus c1 and y is equal to m2x plus c2. The joint equation of these two straight lines is y minus m1x minus c1 times y minus m2x minus c2 is equal to 0. This can be written as y square minus m2 times xy minus c2y minus m1 times xy plus m1 m2 times x square plus m1 c2x minus c1y plus c1 m2x plus c1 c2 is equal to 0. Collecting the coefficients of like terms, we get y square plus m1 m2 times x square minus in brackets m1 plus m2 times xy plus m1 c2 plus m2 c1 times x minus in brackets c1 plus c2 times y plus c1 c2 is equal to 0. Let's denote this by equation 2. Now note that equations 1 and 2 represent the same pair of straight lines. Therefore, comparing the coefficients of like terms in equations 1 and 2, we have the ratio of coefficients of y square, which is 1 upon b, is equal to the ratio of the coefficients of xy, that is minus of m1 plus m2 upon 2h, is equal to the ratio of the coefficients of x square, that is m1 m2 upon a, is equal to the ratio of coefficients of x, that is c1 m2 plus m1 c2 upon 2g, is equal to the ratio of the coefficients of y, that is minus of c1 plus c2 upon 2f, is equal to the ratio of the constant terms, that is c1 c2 upon c. This implies that m1 plus m2 is equal to minus 2h upon b, m1 times m2 is equal to a upon b, c1 m2 plus m1 c2 is equal to 2g upon b, c1 plus c2 is equal to minus 2f upon b, and finally c1 times c2 is equal to c upon b. Let's denote these results by 3. Next, we will determine the point of intersection of these two straight lines, whose equations are y is equal to m1x plus c1 and y is equal to m2x plus c2. Taking the difference of the two equations, we get 0 is equal to m1 minus m2 times x plus c1 minus c2. And therefore, x is equal to c2 minus c1 upon m1 minus m2. Therefore, y, which is equal to m1x plus c1, is equal to m1 times in brackets c2 minus c1 upon m1 minus m2 plus c1, which simplifies to m1 c2 minus m1 c1 plus m1 c1 minus m2 c1 divided by m1 minus m2. In the numerator, m1 c1 cancels, and therefore the value of y at the point of intersection of the two lines is equal to m1 c2 minus m2 c1 upon m1 minus m2. Therefore, the coordinates of the point of intersection of these two lines are c2 minus c1 upon m1 minus m2 and m1 c2 minus m2 c1 upon m1 minus m2. Now the square of the distance of this point from the origin, let's denote it by d, is equal to c2 minus c1 upon m1 minus m2 whole square plus m1 c2 minus m2 c1 upon m1 minus m2 whole square. And this is equal to 1 upon m1 minus m2 whole square times in brackets c2 minus c1 whole square plus m1 c2 minus m2 c1 whole square. This can be written as c1 plus c2 whole square minus 4c1 c2 plus m1 c2 plus m2 c1 whole square minus 4 times m1 c2 times m2 c1 divided by m1 plus m2 whole square minus 4m1 m2. Now recall from result 3 that c1 plus c2 is equal to minus 2f upon b. c1 times c2 is equal to c upon b. m1 c2 plus m2 c1 is equal to 2g upon b. m1 times m2 is equal to a upon b, and finally m1 plus m2 is equal to minus 2h upon b. Substituting these results, the value of d is equal to minus 2f upon b whole square minus 4c upon b plus 2g upon b whole square minus 4 times a upon b times c upon b divided by minus 2h upon b whole square minus 4a upon b. And this is equal to 1 upon b square times in brackets 4f square minus 4bc plus 4g square minus 4ac divided by 1 upon b square times in brackets 4h square minus 4ab. 1 upon b square cancels across the numerator and the denominator. Also, 4 cancels across the numerator and the denominator. And therefore, d is equal to f square plus g square minus c times in brackets a plus b divided by h square minus ab, multiplying the numerator and denominator by minus 1. This is equal to c times a plus b minus f square minus g square divided by ab minus h square. And this is the required result.